All right, so let's go ahead and get into this Thevenin and Norton example problem. I'm going to go ahead and draw out the circuit. Just put a resistor here, and then let's throw a current source here, resistor here, and then I'll throw my load out here. How about that? Actually, this is a little complicated. Let's not get into anything crazy like this. It's going to take a while. I'm trying to keep these videos pretty short. Let's just go with a resistor there, and then we'll just throw our load resistor right here. We'll ground this. This will be my load resistor. And let's go ahead and call this a 9-volt battery. We'll put 1K, 2K, 3K, and then I'll make my load a 1K as well. Actually, let me draw it in red. Okay, and so the first step of any Thevenin and Norton problem, I didn't really list it here in the steps because it's not part of finding the equivalent circuit, but it is important for validating your equivalent circuits. And that is that we need to determine what the load voltage and load current are to begin with, okay? And so let's just make that the first part of the problem. Basically, I'm going to need to solve this circuit to determine what's the voltage here. We'll call it Vx, or actually let's call it VL, and we need to know IL as well, because what we're going to do is we're basically going to remove the load from the circuit like we said. Then we're going to find an equivalent Thevenin and Norton circuit for the rest of this stuff. And what we're going to do at the end is we're going to put our load resistor back into our equivalents and make sure that the load voltage and load current match, because if they do, then that means that we correctly determined the equivalent. Okay, so let's do that first. What we're going to do is let's label this 9 volts. We know that that's 9 volts. And what I can really do is I can recognize that my 3K and my 1K load are actually in series here. So I can combine them into a series resistor, which would give me 1K here. I'd have 2K here. And then the 2 in series gives me a 4K. And now I have a 2K and a 4K in parallel, which I can go ahead and solve for. 2K times 4K is 8 divided by 2 plus 4. That gives me 1.33K. And then I have 1K here. I know this is 9 volts, and I can go ahead and solve that voltage divider. I'm just going to do it real quick in my calculator. 9 times 1.33 divided by 2.33 gives me 5.13 volts right here, which is this voltage. 5.13 volts. And now I have another voltage divider, my 5.13 volts with my 3K and my 1K. Okay, so let's go ahead and do that real quick. 5.13 times 1K over 4K basically is, you just divide by 4, 1.28 volts. That gives me VL. So my VL to start that I should be looking for when I get my equivalent circuits later on is going to be 1.28 volts, and all I have to do is divide that by 1K to get my load current. So my IL, when I'm looking later on, should be 1.28 milliamps, okay? So this is the first step of the problem, is kind of just solving it to determine the load current and the load voltage. This wasn't meant to be instructional, so if I went a little fast, I'm sorry. This is really just meant to give me the VL, the VL and the IL that I'm going to use to validate my equivalent circuit. So let's just stop this video here, and in the next video I'm going to go ahead and actually solve for the Thevenin and Norton equivalents.